So we just looked at how a linear system behaves if we slightly change its initial conditions or we slightly change parameters of the system. And we discovered, at least through this example, but in general it's true, that if we change those a little bit, the behavior of the system by and large doesn't really change too much. And it's still going to go back to that equilibrium position if we have an autonomous system. We give it some initial conditions, let it go. We have no external forcing. We'll address that later. And really this was done as a setup to contrast linear systems from the nonlinear systems that we're about to look at. So I just want to set it up with a little adage I came across, that if you do not give people an example, they do not understand the point. But if you do give an example, they think the example is the point. We're going to be looking at the Lorenz system as the classic nonlinear system to investigate some of the differences between linear systems and nonlinear systems. But one, I don't want you to be under the impression this is the only nonlinear system. And I'm using this as the example because it's really the first one that was thoroughly investigated, and also it really amplifies or exaggerates some of the properties of nonlinear systems. Not all nonlinear systems are going to behave as dramatically as this system does. Some nonlinear systems will behave more or less like linear systems, but this is being done to show the point of what can happen in nonlinear systems. However, I don't want to just talk abstractly about these nonlinear systems. I want to be able to show some plots, some animations, so that's why I'm going with this one specific example as we go forward. So, with this out of the way, let's look at the nonlinear system we want to investigate. So we're going to be looking at what is called the Lorenz system, which I'll get to in a moment here. And it was developed or really investigated by Edward Lorenz. So I'll begin with a little bit of backstory of how this system became interesting to Edward Lorenz and why we are still investigating it today. So I'm going to give a brief version of the story, and some of it is probably simplified, some of it is going to be a little bit changed for convenience. You can get a lot more information on videos I've embedded in the website. They'll go into really more of the detail, but I want to get kind of the broad strokes out so we can understand the nonlinear systems we're going to be looking at. Edward Lorenz worked in the field of weather prediction and weather modeling, and they were looking at these systems of ordinary differential equations that were able to make predictions about different aspects of the weather: the temperature, the humidity, air pressure, wind speed, things of that nature. And then they were ordinary differential equations. They were able to solve them numerically and then forecast into the future what the future temperature, wind speed values were going to be. And like any other ordinary differential equation, if you knew the initial conditions, you could then solve it going forward. So he was working with a particular set of initial conditions and the equations, and this was in the early days of computers. So he put the initial conditions into the computer, let it run. It probably took a while, so he came back and he looked at the results, and then he wanted to just validate these results. So he goes back to the computer, puts in the same initial conditions, and lets the computer run while he goes out, gets a cup of coffee. And when he comes back, he notices that the final results of these predictions, a couple days out, let's say, were different on the second run than the first run. Well, because these are ordinary differential equations, because the solver he's using is going to be using the same process each time to make these calculations, there really should be no reason that the second result should be different than the first result, because nothing in the system itself is random. It's all completely deterministic. However, if we looked at let's say the temperature 15 days out from the second run versus the first run, they were very different values. So going back, kind of recreating his work, he saw that the initial conditions he put in, the second time he made a very small error in one of the initial conditions. So let's say it was supposed to be 15.00001, and he had 15.0002. Right, so as a percent difference, it was a very small change from the first run to the second run. However, when it was put through the computer and forecasted out several days, it turned out to be a big difference in the final value. So this system was showing what we call a sensitivity to initial conditions. A very small change in the initial conditions resulted in a large change in the forecast. Now, contrast this to what we saw in the linear system. We made small changes to the initial conditions and noticed small changes to no changes in the forecast as we pushed the solution forward in time. And the same thing was true with the parameters in our example. We changed them a little bit, and we saw no real differences as we went forward. So, at least in the big picture, this was the first time that the sensitivity to initial conditions was really noticed and then further investigated, was using this weather system. And this can crop up in nonlinear systems. And this investigation, the subsequent work, led to the field of chaos theory, nonlinear dynamics to really be studied in and of itself. So what we're going to be looking at is a simplified version of this weather model that Lorenz was working with. So we've reduced it down here to just 3 state variables, x, y, and z, or 3 states, x, y, and z, which will result in 3 state variables, and then these constant parameters, sigma, rho, and beta. Now, what these states actually represent, it doesn't really matter too much because we're really looking at the math behind this, not of the physical modeling part that got us these state equations. But let's just, for the sake of argument, say that x is the temperature, y is the air pressure, and z is the humidity. And let's say that the time scale we're working with, the base time, is going to be days. So if we're looking at t equals 5, we're going to be looking 5 days out. This is not meant to be an accurate model. This is just kind of so we can think about what are these variables going to be representing and what's the time scale that we're talking about. So if we notice this reduced equation set, these 3 equations, it's in state space form already, in that the derivatives of my state variables are isolated on the left-hand side. Again, we have 3 states in this case. There's no second derivatives. So I have x dot, y dot, z dot by itself. That's what we want for our state space model, like we saw in linear systems. However, when we look at the right-hand side, well, the first equation for x dot, we have a sigma y minus a sigma x if we were to distribute it. Well, that's fine. Sigma is just a constant value, so that's linear. If we look at the y dot, however, we have, let's say we expand that out, rho times x, that's okay, rho is a constant, minus x times z. Well, we didn't encounter this before in linear systems. Since they were linear, we have a state variable times another state variable. That makes this a nonlinear system already. And then we have that minus y, that's okay. But we do have an x times a z, so that presents a problem. And for the z dot equation, again, we have this x times y, both of them state variables being multiplied. We have z dot is also this nonlinear equation. We cannot represent this in matrix form with that like x dot equals ax plus b, or in this case it's autonomous, so just x dot equals ax, because we can't make an A matrix when we have nonlinear equations. So we're going to see a little bit how we set this up so that we can solve it numerically in MATLAB, or a lot of other solvers are going to operate in a similar way. We can still use tools like ODE45 to solve this. The difference is we can't set it up in matrix form. We're going to have to explicitly put what the x dot, y dot, and z dot equations are in order for ODE45 to be able to handle it. And also note we have these parameters, constant parameters, sigma, rho, and beta. Those could be collected experimentally or maybe have a physics basis for it. They're just relating the different variables. So think of them again like a spring constant or a damping coefficient, but just for this particular weather system, that's what those parameters are. Now we'll get into the actual MATLAB simulation in the next part, but let's just look at, for this reduced system, what does the state space look like? So what I'm going to do is solve for x, y, and z going forward in time, and we'll see the initial conditions and the parameters that we're going to be using. All right, so this is the really nice picture that comes out here if we use these particular parameters, a rho of 28, sigma of 10, and beta of 8/3. And here I'm just saying my initial conditions that x is 1 at the start, y is 0, and z is 1. All right, so if we solve it using ODE45, and this was simulated for t equals 0 to t equals 50. So again, let's say this is making predictions 50 days out. So what we're seeing here is the relationship between our state variables. Let's again pretend it's temperature, humidity, air pressure. We see we're going to be starting at our 101, and then we follow this trajectory around, and it makes this kind of butterfly shape where it's circling around these 2 points in space as we go forward in time. Now this is a little bit different than the linear system we looked at before, because given enough time, our linear system, the energy dissipated out and we got to some equilibrium position. This nonlinear system is different, that we're not really losing, let's say, energy in the system, generic energy. This will keep rotating around over and over again, as we're going to be seeing in the animation, and it's not going to settle to one constant value in this case, but it will keep repeating around these points. So what we're going to look at next is, well, what happens if our initial conditions are slightly different than 101? And then we'll follow that with, well, what if our parameters are a little bit off?